and that cement, as is popularly known, 1 ton of cement produces 1 ton of carbon dioxide, which is not true right now, but we will. So what they say is, because it is using cement, and cement happens to be enemy number 1, concrete also happens to be enemy number 1, which is not correct, because we use only 10 to 15% of cement in the volume of concrete. And in the cement also, this 1 ton per cubic meter of cement is an old story. Now there are things which are different. I'll come to that later. So when you consider any material as sustainable or otherwise, we have to look at the life cycle, which consists of extraction, processing, construction, operation, demolition, and recycling. All of these operations, what is the amount of energy that is consumed? What is the energy that will be consumed during its lifetime, as well as the carbon dioxide equivalent emissions that are there. So based on that, if you study most of the materials which are available now as alternate to concrete, it appears that we have no choice but to use concrete, and concrete is not such a bad enemy after all, from the bottom line of environmental, social, and economic sustainable development tenets. Still, we want to make that concrete more sustainable, or as sustainable as possible. And the route that we can take is to make cement more sustainable. That is, use less energy intensive kilns, or use supplementary cementitious materials to reduce the clinker component. Here I would like to say that this concept of 1 ton of carbon dioxide for 1 ton of cement was in the era of ordinary Portland cement being called as cement. Today, cement has sometimes more than even 50% of alternate materials which is there in the cement, which is called blended cement. So for example, if you use fly ash, up to 35% of the 1 ton of cement happens to be fly ash, which is not contributing to carbon dioxide emission. Or if you are using slag, GGBS, which will be probably upwards of 50% of the volume of cement. So if you can, and also this in fact enhances the quality of concrete and contributes to sustainability. So one is to make cement more sustainable so that we produce more and more blended cement rather than ordinary Portland cement, and keep ordinary Portland cement reserved to only where you require certain high strengths and high performances in structural requirements. Anyway, there are also possibilities that we use new types of clinker. So there are like belite calcium sulfoaluminate ternocite blends which people are looking at, which gives you a totally different type of clinker which has lesser carbon dioxide footprint. And also to use alternative fuels and renewable energy during the production process. Of course, there is an expert from the manufacturing who will be speaking on this from Dalmia. So I would not delve into the manufacturing processes and how sustainability things have been taken care during construction. So there is also an attempt to see if we can produce clinker-free cement. So clinker is the one which is bringing in the harmful things like emissions and also energy consumption. We are trying to see if you can manage without clinker a cement. Now coming to concrete, the alternative materials people are looking at in concrete are recycled aggregates, secondary aggregates, and then utilization of wastes in concrete, either as reinforcement or as special additives. Attempts are also on to make the concrete more durable, because the longer a building or a structure lasts, the lesser will be the consumption of cement or concrete or both, and hence sustainability is said to be achieved through longer lasting structures. So this is also vigorously being pursued, and then capturing or sequestering carbon dioxide in concrete, or capturing carbon dioxide and storing it underground in bedrocks and so on and so forth. This is another route that people are trying to pursue. And they are also trying to see if we can go for clinker-free concrete like geopolymers, etc., etc. So how people are now trying to attempt the reduction of carbon dioxide as mentioned, by 2050 or 2070 or whatever. So there are several attempts. A few of them I would like to very quickly go through because the time allocated is only 25 minutes. So I would like to highlight certain things. It's neither exhaustive nor complete in that sense, but whichever is priority according to my limited knowledge, I have tried to come here. So now, first thing that I would like to highlight or show is about the Global Cement and Concrete Association's initiative. This is called the GCCA Initiative. This was unveiled on September 1, 2020. 40 of the world's leading cement and concrete companies, including several leading cement companies from India, have signed this pledge, and they have a roadmap that they are now trying to put in place. So the ambition statement of GCCA demonstrates that there is a commitment of the industry across the globe to drive down the carbon dioxide footprint out of this particular material, which is the world's most used man-made product. So with an aspiration to deliver the society with carbon neutral concrete by 2050. So the statement identifies the levers, because there are several things where they are trying to tackle, and those levers which are right now creating this nuisance, they are trying to turn them so that we get a much better concrete or cement or both. So to achieve this carbon neutral concrete, some of the lines that they are thinking of is, as I mentioned earlier also, reducing and eliminating energy related emissions, which is connected to the manufacturing sector, reducing process emissions through new technologies, deployment of carbon capture, more efficient use of concrete, reuse and recycling of concrete in buildings, harnessing concrete's ability to absorb and store carbon from atmosphere. These are the lines on which the GCCA is very vigorously working along with the industry partners. So one such initiative which came much before GCCA is called the European Cement Association or Symbureau's framework. This is called the 5C framework. 5C framework, the 5 C's are C for clinker, C for cement, C for concrete, C for construction, and C for recarbonation. So these are the sectors in which people are trying to work, and they are confident. Of course, this is a very detailed document available on the net if anybody wants to see how they are planning. The Symbureau is planning this 5C approach and reducing. In 1990 itself, the carbon dioxide emission, as you can see in this picture, is 783 kgs per ton of cement. So it's already reduced from that so-called 1000 kg per 1000 kg of cement to 783. It had reduced in 1990 itself. So from that level to bring it to zero at 2050, the 5 C's are in place. That is through the cement route, through the concrete route, through the construction carbonation route, through reduction in emission route, and clinker route, and so on. So carbon capture and utilization is one approach. Carbon capture and storage is another approach. So this is what Symbureau is attempted to do, which most of the European countries are following. Of course, GCCA is a much bigger worldwide body that now has come into picture from 2020 onwards, and India is also participating through that route. There are some approaches which I would like to quickly highlight for upcycling the carbon dioxide. Hundreds of companies and research groups are working on this to keep the carbon dioxide out of the atmosphere and store it in some place, including geological formations, soil, soda bubbles, concrete blocks, and so on and so forth. And also they're trying to make waste carbon dioxide into something which is marketable. So this carbon dioxide, if somebody is going to put into use and it can be marketed, and that will be a very nice way to make sure that it doesn't get into the atmosphere. So entrepreneurs can begin raising revenues needed to scale their technologies by making this marketable. So there is also possibility that carbon dioxide, mineralization is possible by capturing the carbon dioxide from several, not only cement, other industrial emitters also, purify them, store them, and distribute to concrete producers in pressurized tanks. So these, purified liquid carbon dioxide, which is there kept in stainless steel drums in the RMC yards or ready mix concrete producing manufacturers place, it is injected into the wet concrete mix using a patented technology, and the carbon dioxide reacts with the calcium ions from cement to form nano-sized mineral calcium carbonate, which gets embedded in the concrete. So the result is that we get a stronger concrete, we get a better mix optimization with a reduction in the cement consumption and also consumption of carbon dioxide. To the extent people are expecting that about 500 million tons of carbon dioxide per year can be sequestered or captured and put into good use into concrete. Just like as I mentioned earlier, when we add mineral admixtures to cement, it's not an adulterant as many people think it is. In fact, the introduction of either fly ash or slag improves the performance of the concrete in terms of strength as well as durability, like capillary closure and better performance against acids and so on and so forth, and reduction in the corrosion of steel, etc. Similarly, here by inducting or inducing liquid carbon dioxide into the concrete mix, we not only consume carbon dioxide, but we also improve the quality of concrete. So this technology can be retrofitted into any existing concrete plants, and many attempts are happening of this approach in India as well. Not only injection of carbon dioxide, there is also a possibility of curing with carbon dioxide. So again, the idea is to get a much higher strength and better durability in this. So this is something which has been proved and is also now several RMC plants across the world are trying to improve on this particular system. There is another approach which the Institute of Carbon Management of the University of California, UCLA, is proposing. This is locking flue gases of carbon dioxide into limestone within the concrete, a little different approach from the previous one which I mentioned. So this is also something which now is getting popularized. This is called the Reversa technology, again patented right now. So it's a low-cost solution for thermal energy, cement, and steel for the incinerator operators. So the Reversa process reduces the emission through a combination of utilization of carbon dioxide by permanently embedding it, and also avoiding, that is reducing carbon dioxide emissions associated with the raw materials. So this modular technology again can be added to a site or permanently embed the flue gas of carbon dioxide into masonry or precast concrete produced nearby. So during the curing process, carbon dioxide is directly injected from flue gas streams like power plants or cement factories directly without storing it, put concrete manufacturing industry next to these carbon dioxide producing plants and directly feed that into the concrete mixture where it is chemically transformed and permanently stored. So there is also another project called Project SEM0, which is a Swedish project by Cementa and Vattenfall. This project introduces a lot of studies and prototype experimentation on calcination and clinker material formation for carbonate-based raw materials under the electrical heating approach, carbonation under cooling in high carbon dioxide concentrations, and then evaluating technologies aiming at upscaling and determination of gas composition. So the suitability of gas capture, transport, and geological storage is being evaluated. The three thrust areas that Project SEM0 is focusing on is on heat transfer with plasma in rotary kilns, direct separation of carbon dioxide from calcination of carbonate-based materials, and carbon dioxide-free products with electrified production. And then nanomaterials, everybody is getting into this area. Carbon upcycling technology transforms the residues such as fly ash and slag, making them more reactive and increasing their cementitious properties, which means we can incorporate more of these materials into cement, thus reducing the OPC content within the cement itself. So the use of carbon dioxide previously captured combined with physical transformation, can create a new addition to the cement that allows for production of concrete. The improvement obviously is evident for everybody. And there are other approaches which many companies are using. This is one another approach of heating it. The portion which heats the clinker to 1450 degrees centigrade is the one which they are attacking, and they are trying to see whether we can do heating free activation process by alkalis and things like that, so that we avoid that heating process and also reduce all the attendant carbon dioxide emissions and so on. So this manufacturing process by a company called Hoffman Cements is also now trying to do the approach of valorization and production so that we can use this particular cement for concrete. So there are various types of cement that they have already produced. One is called HP2A cement. I'm not getting into the details of this for want of time, but they have already started producing prototypes. As you can see, ready-made stairs, ready-made roofing, ready-made blocks, and so on and so forth. Even wall panels and so on. They are already into production, commercial production, and this is also called as green cement, green concrete by them. So there are many approaches using even gypsum and so on. I'm not getting into these. They're also trying to see if they can produce a cement, zero cement concrete kind of thing. This work is happening in Australia, where they are trying to see if they can avoid this concrete corrosion that happens in sewage system by using nanosilica, fly ash, slag, and hydrated lime. And it's a very environment friendly approach that they are taking. So lastly, I would like to talk a few minutes on this LC3, on which the BIS has already formed a working group, and the draft code for LC3 is almost ready. This is basically calcined clay limestone cement. So this particular limestone calcined clay cement is a good combination of using calcined clay, and the clay that we use here are not the superior kaolinite kind of clay which is required for the ceramic industries and so on. Slightly lower grade clay which is now getting wasted can be incorporated here, and this calcined clay can be a very good input into the manufacture of cement. So this is going to pick up in the coming years, right? Even in India also. This is led by a Swiss group, which is called the Swiss Agency for Development Cooperation, and 2-3 IITs from IIT Delhi, IIT Chennai have collaborated with them, and even some universities of Cuba, Brazil, etc. are there. And the Indian cement companies are very vigorously pursuing this. The basic flow chart is to find suitable clay, process it, calcine it, and then there are two routes. One is blended with the clinker, along with limestone clinker and gypsum, or blend or intergrind with the one is called LC2, where there is no OPC content. It is just a blend of calcined clay and limestone. Keep it, it can be there for any number of years without any problems of hydration or whatever. You can add OPC whenever you want and you get your LC3. In LC3, we have clinker, which is ground along with limestone and calcined clay, and you have a cement, which is called the LC3 cement. So both of them are likely to come in a big way in India. So I would like to probably right now end with this. Just last thing is about the concrete construction practices, which also need to be looked at from the Indian perspective. See, the majority of concrete produced in India is by an unorganized sector, which is a big difference between what happens in Europe or in America, where everything is a ready-mix concrete. It is done under good supervision and good quality is there. So we have to see how we will introduce these concepts into the concrete, which is manufactured largely by, of course, a lot of it is now becoming organized sector, but how to handle that is to be looked into. Virtually no awareness is there about sustainability aspects, either in the client's mind or in the concrete producer's mind or in the contractor's mind, how to drive these issues into their mind and make them responsible. Environmental regulations also are inadequate and not enforced effectively. Engineered or semi-engineered constructions are limited to large housing or infrastructure projects, and use of ready-mix concrete is just about 10% of the total concrete produced. So all of us have a responsibility to make sure that more and more scientifically produced ready-mix concrete is used, and we need to minimize wastages of these crucial natural resources by making the effective judicious use. So construction industry has a large role to play, and several groups of different countries have tried different approaches with varying degrees of success. And durability is one of the important factors that is being looked into other than QA/QC procedures. Thank you very much for the opportunity given.
Thank you. Thanks a lot, sir. And as I am sorry, there was a little bit trouble in my network connection, so I would like to give a little bit introduction of Sri Kalgal Sahab.
No need.
He is basically ME in no need. Okay, sir. Okay. Thanks a lot, sir. Once again, now I would like to invite Sri Ashish Singhai ji. He is basically BE Civil and has done PG in marketing. He is a member of lot of associations, including Indian Civil Concrete Institute, Institute of Elias. He is also affiliated with Rotary Club of Indore. He is currently working as general manager with Gcca Cement at Indore. And he is a visiting faculty to more than 20 institutes all over India. And he has till date given presentations and lectures in around 48 technical and management institutes across India, and addressed over 3,000 students on soft skills and engineering subjects. He is technically trained to 1,200 engineers and architects, 3,300 civil contractors and paint contractors. He has given presentations in over 65 different central and state government departments, PSUs, and various private enterprises, totaling to over 2,500 participants on technical subjects. Sri Singhai Sahab. Over to Singhai Sahab. Singhai Sahab.
Ashish, you are muted.
Yeah. Okay. Am I audible?
Yes, sir. Yes, sir.
Yes.
Okay. Very good evening to one and all, and a special thanks to Dr. Pranay Gandhiji and Dr. Shilpa Tripathi on behalf of Institution of Engineers. And I am extremely privileged to be in front of such an august gathering, and especially I had the privilege of sharing the forum with Dr. Kalgal sir, whom I always respected as my guru all through my life, and Mr. G.V. Ramakrishna ji. So once again, on this outset, I welcome all the fellow students or the listeners who are listening to us today, and a very warm greetings to one and all. So first of all, thank you very much, Gandhiji, for such an elaborate introduction, and extremely privileged for being here.
Welcome.
Yeah.
Welcome, sir.
So, so what I'll do, I'm just going to share my screen, and please let me know once it is done. Yeah.
At the bottom of your panel, please share your screen to the green button, sir. Share screen.
Yeah, I know, sir. I know. So is my screen visible now?
Yes, sir. Kindly make it full screen, sir.
Okay, I'm just doing that. Yeah, is it now visible?
Yes, sir. Thank you, sir.
Okay. So now, so we speak. We start my presentation, which is on the same topic, sustainability issues in cement and concrete industry. And as Dr. Kalgal sir has already elaborated quite a bit on this burning topic, and it would be again my pleasure to add on to what I have learned all through my life. And Dr. Kalgal sir has introduced us to some very latest technologies and emerging trends which are being taking place across the globe for sequestration of carbon dioxide emission, which is at this point in time one of the very important factor to be looked into, as we are all witnessing global warming, and mission 2050 has been taken up very seriously across the globe. Yeah. So I start as now we all know sustainable development. What our industry experience says that it is basically meets the need of the present without compromising the ability of the future generations to meet their own needs. It has to be always local. The simple meaning is that if we import the designs, technologies, products, or materials from far-fetched distances or from other countries, possibly the very purpose of sustainability fails. Sustainability is all about preserving the current reserves of the resources without damaging or deteriorating the future requirements or the needs. So this is all as Dr. Kalgal sir has already elaborated on these three pillars: environment, society, and economy, above which the sustainability rests. Okay. So what do we exactly mean by sustainable development, and why the entire world is looking into it? Why specifically cement industry or the concrete industry as such is being now targeted for that? Because we are perhaps the largest contributor to the carbon dioxide emission in the global system. So as we all know that concrete is single largest man-made material being produced and used in the world, and it is the largest contributor to the carbon dioxide emission. So if we can make judicious corrections in CO2 emissions in cement as well as in concrete, to the larger extent, the globe can ensure the sustainability aspect of this from the construction industry. So if we can make the development of the construction in such a way towards sustainability, it will improve the life, it will protect the environment. We have got energy conservation, waste reduction, efficient use of natural resources. That means conserve, preserve, and improve the longevity, better operational performance, etc., etc. So all these factors shall be covered in the later slides in one way or the other. Now, the green materials is going to be the thing to be talked about. So what do we exactly mean by green building materials? More of the materials to be used in construction. Energy. So any green building has to have optimized energy. There has to be some limitation of utilizing this electricity, which is man-made or the artificial electricity. Any artificial electricity that we are using is an outcome of fossil fuel consumption. So how to minimize, how to optimize? Then after the energy, water and other natural resources during the entire process of construction, operation, and afterwards the demolition. So all these three factors, we have to optimize the use of electricity and water so that buildings are designed as per the energy efficiency. Third point is renewable energy. Why to go for the fuel based energy or electricity? Why not we are shifting towards solar or hydel or the wind power? These are the different three options in front of us. So we can very well switch or at least partially convert our energy consumption towards solar, hydel, and wind power. Fortunately, India is one such country which is blessed with a lot of solar radiations. So solar energy is definitely picking up in a big way. our respected Prime Minister has a big mission on this solar power energy. A lot of big projects have already in operation. A lot many are still under implementation. So we could well be one of the largest solar power producing country going forward. Hydro power, again, we are blessed with some very good rivers or the falls wherein hydro power is being generated. It's 100% green natural energy. And as far as wind power is concerned, we have taken already some very big steps into it. So put together all these three different types of natural energies is going to replace to a significant extent as far as fossil fuel-based energy is concerned. Water positive. That means catering to all its water demand through sustainable processes such as rainwater harvesting, treating and recycling the wastewater on the side if possible, and then again making it back to the system of construction activity. So such buildings can very well be termed as green buildings. What are the other factors? Recycling, reusing of the waste, ensuring that all the waste material is managed on the site itself, and generating optimum waste so that they can be processed locally. Sometimes we see that material is being called upon exorbitantly, and then once it is not used, it is just thrown like that, and it is not only creating a lot of menace and issues and problems to the municipal system, but at the same time it's a national loss as well. So we need to be very, very practical and optimizing all those resources. As we all know that carbon emission by different sectors. So in the very first instance, I told you that almost more than 1/3 of the carbon dioxide emission is contributed by construction activities. So it is absolutely alarming. Apart from construction industry, manufacturing industry is almost 30%. Transport is again a big contributor, close to 30%, and the rest of the industry put together is 10%. But out of which all these 4 different categories, our own construction industry, largely cement, steel, and different building material manufacturers, and the overall construction which is happening across the country or across the globe rather, it is contributing to a significant percentage of up to 40%. So we need to mitigate, we need to design such methodologies, we need to design such processes, such technologies, putting into use such building materials which are not only sustainable, but at the same time contributing least carbon dioxide emission. And as Dr. Kalkar sir has elaborated wonderfully that a lot of research work is being conducted across the globe on some very latest technologies where the capturing of carbon dioxide is going to be done, sequestration of the carbon dioxide is going to be done, and it can be put back to the system, and not only the carbon dioxide emission can be absorbed and captured, but at the same time the same carbon dioxide can add to the reduction of cement consumption itself. So it is going to work in 2 different ways, and ultimately the vision, mission, and the ambition of the globe that by 2050 we can have net zero carbon dioxide emission. So we can very well vouch for that, and every single person is a stakeholder in achieving that mission. Moving on to the energy contribution. The energy of construction can be calculated and optimized through planning, designing, construction, and substitutions. So these are very well known facts. I will just quickly go through the headlines of all these points. Reuse buildings instead of constructing new ones. If at all is this possibility that existing setup, however old it may be, can be renovated. If it is structurally strong, habitable, let us renovate it and start using it instead of going for altogether a new building. Specify low carbon concrete mixes. This is going to be a game changer. When we talk of low carbon concrete mixes, those who are civil engineers and those who are concrete technologists, they can very well understand that we can go for the optimized fly ash, slag, or a combination of slag and fly ash. These are the secondary cementitious materials embedded into the concrete, whereby we can produce not only a low carbon dioxide concrete mix, at the same time it is going to be economical and sustainable as well. Third point, which comes to in continuation of that, is limiting carbon intensive materials. As we all know that a lot of aluminum, plastics, foam insulation, paints, etc. These are the materials also being used during a construction of a building or for that matter for any project. So how we can minimize the use of aluminum, plastics, foam insulation, paints, etc., which are high carbon footprint materials. So we need to be, the architecturally we have to think in these directions. Reusing the materials wherever possible. Let us salvage the materials like brick, metal, broken concrete, or wood. And I salute to a few of the green consultants and architects who have been doing wonderful, planning for the new construction also, where they are salvaging all such materials and bringing it back to the construction system. So we are to a larger extent limiting or constricting the carbon dioxide emission. Then the fifth point says that using high recycled content materials. So it is especially important with metals. Virgin steel has high embodied carbon footprint, almost to the tune of 5 times greater than the high recycled content steel. So we can mix and match different product categories. What is to be used, what not to be used at all, and if at all it is to be used, how can we replace with some low carbon footprint material. So it is all about wonderful planning by the architects and structure consultants. Using fewer finished materials. Now it has taken off a fancy, and few of the structure consultants have started designing the buildings with good concrete finish. That means they are not putting up any paint, putty, or for that matter, any such embellishments or finishing on their buildings, wherein the carbon footprint of such materials is higher. So it can very well be avoided, and the natural concrete finish, it is also a beauty. As we all say, that fall in love with the concrete. The concrete itself is a beautiful material. If it is properly prepared with love and all the technical parameters, the finish of the concrete says it all. So nothing can replace. It is not always necessary that concrete has to be embellished or it has to be, aesthetically, beautified with a good quality putty or good, very high-end kind of paints and all these things, which at the, at the end of the day can lead to larger carbon footprints. So that means we can, have different kind of mix and matches during our construction strategies. Minimizing the waste. Always order the quantity to the extent of consumption. Now, embodied energy is a very, very good concept of establishing how much EBE has gone into to produce one particular product. Let us take the example of cement. Cement is a mined material. It's the primary raw material is limestone, which is mined from the mines. So right from the mining and extraction of the limestone to the finishing, which is being done after the process, to the finished material, then transported to the final end customer through a delivery system. So mining, there's some quantum of energy will go into mining of the limestone. Some quantum of energy would go into manufacturing from limestone, conversion of limestone to the cement. Some energy will definitely go towards fuel and transportation. So that is transportation energy. And finally, to the product delivery. So the put together of all these 4 parameters would add to the final EBE of cement. Likewise, for every single material, EBE is calculated and designed. So what we should do as a carbon dioxide emission to prevent the carbon dioxide emission in our construction strategies and planning, we need to go for low EBE materials. As simple as that. Now, how to do that? The best part is that let us calculate EBEs of all such products and then choose whichever has the least one to be prioritized and to be used in bigger quantity. So this embedded energy in material is defined as the energy required in making a product. The more embodied energy value, more is the carbon footprint of the product. So this single number of EBE, gives a complete scan of that particular product. And let me tell you, in Indian affordable houses, less energy is in operation and maximum energy requirement is during the construction stage. So during the operation, energy could be less, but during itself, it's preparing of this material itself and using it in the construction stage, a lot of energy goes in the system. Buildings are primarily responsible for 40% of the global energy use and contribute towards 30% of the CO2 emission, as we just saw in the previous slides. Cement and steel, which contributes to roughly 30 to 32% of the total building material out of construction of a house or a project. So they have very high embodied energy material. But does that mean that we should stop using cement and steel? No, it cannot be the solution. For the construction, for the economy, for the sustainability of the any economic system, the construction activity has to be there, because still in India, construction is second largest employment generator, just next to agriculture, and going forward to few years, possibly it might exceed the your agriculture employability also, and still one of the largest GDP contributor. So construction has to be there, and without cement and steel, it is not possible. But only thing is that we need to have a very conscious approach towards the EB. For example, cement has 6.7 mj per kg. Steel has about 4 to 5 times of that, 32 mj per kg. Let us have comparison how we can replace the low EB for high EB. AC block, now it is very much in the custom, very much in the fashion, being used extensively in major cities as well as in the tier 2 cities also. So AC block has just 0.6 mj per kg, whereas the typical red clay bricks has almost thrice, that is 1.64 mj per kg. So it's a very conscious decision that we can take, replace fire clay bricks from AC block. Similarly, instead of going for OPC, let us switch to either PPC or slag cement or the triple blend cement during the concrete, so that we can minimize the carbon footprint on account of EBE calculations. So hence, among all these, steel is very high in embodied energy values, and if quantity of steel and cement increases, the EBE content goes manifold. Just a chart which shows EBEs of different products. As I mentioned that fired clay bricks is 1.64, whereas AC block is almost 1/3. Just look at that alarming and screaming red values. Aluminum is as high as 170. Acrylic paints, which we always passionately choose for our new houses, is almost 62. Plastic 90. Just look at steel. Anyway, it cannot be avoided. 32. Cement cannot be avoided, but if we go for blended cement, it could be significantly low, to as low as 3.5 to 4. So there has to be a very conscious call on EBE, and I would urge all the structure consultants to have a very fair understanding on EBEs of the building materials that is being used. Aluminum can be minimized, acrylic paints can be avoided, plastic can very well be get rid of as far as any new construction is concerned. So we can always shift from high EBE products to low EBE products, because it has a direct connection with reduction in carbon dioxide footprint. As we have been just mentioning again and again, by 2050, the global mission is to decarbonize the world's built environment. Decarbonizing, that means making net zero the world's built environment, and to meet global climate change goals. A lot of efforts are being done, a lot of global efforts, a lot of research, a lot of publications are being published. Technologists, scientists are banging their heads together, and I'm not surprised if the 2050 mission could be achieved earlier than that. So we are all keeping our fingers crossed, and we are all looking forward to this mission of decarbonizing the world's built environment much before than 2050. Green concrete is again a reply to all these things. It uses waste material as at least one of its components, or its production processes does not lead to environmental destruction. So if we can use the waste material and just embed in our concrete system, it can be made green. The next point is carbon sequestration technology, which has been elaborately and wonderfully explained by Dr. Kalgal sir, and we can always look forward to that. mineralizing the atmospheric carbon dioxide and injecting it into the concrete mix, thereby reducing the amount of cement required in building projects. So what we are doing, we are going to have a twofold benefits. Not only atmospheric carbon dioxide is being captured and mineralized, injecting it into the concrete mix. So reduction of the carbon dioxide, at the same time, the cement requirement is also being reduced to a larger extent. So this is carbon sequestration for you. We have environmental benefits like using green concrete, last longer, reduction of energy consumption, etc., etc. Advantages manifold, as we have been mentioning again and again. Method of preparation of green concrete is same. We need not to have any R&D for that. Just by just a common kind of a mix, the green concrete can be mixed. Reducing the environmental pollution, good thermal and acid resistance. It reduces the consumption of cement, economical, and has a better workability. So some green, smart, innovative cement and concrete. I will just mention the names. I cannot go elaborately because one more very expert panelist is about to enlighten all of us. So I will just throw a small light on that. Gandhi sir, am I audible and visible? Vinay ji?
Yes, sir. Yes, sir. Yes, sir.
Okay. And sir, could you just let me know how much time I can still go for, because it is 7:15. If time is not a constraint, please let me know. If this is a constraint, please also let me know.
5 more minutes.
Fine, sir. That's fantastic.
5 or 10 minutes. You can also take 10 minutes.
Fine, sir. I'll just try to wrap up before that. Okay. So blended cement, nothing new. It reduces embodied energy due to fly ash and GGBS. Translucent concrete would help us in minimizing the artificial light required. So let the natural light come in our buildings. I will just give few slides that will elaborate that. Pollution eating concrete, aerated autoclave concrete, that is AAC block, which is the India's first green building material, listed and rewarded by Indian Green Building Council. And I had the proud privilege of getting this reward for my earlier organization. So that was practically the first IGBC awarded by the Green Building Council of IGBC as the first 100% genuine green building product. Afterwards, many more products have get into the list. Manufactured sand, instead of going for the river sand and murdering the rivers, we can always go for the crushed aggregate sand known as manufactured sand, which being used extensively all across India now. Pervious concrete for the rainwater harvesting and recharging, and geopolymer concrete, that is cement-less concrete. That is going to be a game changer for the concrete industry. No cement is being used, yet you're going to produce a concrete with very good strength, durability, longevity, sustainability, because we are going to use either fly ash or silica, GGBS or fly ash, but we are not going to use cement. So this is going to be a game changer, and significantly it can reduce the quantum of CO2 emission in the global atmospheric system. So these are the things that I cannot go in great detail because the time is not permitting me to do so. Fly ash we get from thermal power plants, GGBS as a waste material from the steel industry, and apart from that, silica fume, metakaolin, these are the secondary cementitious material. Rice husk, as parali is one of the biggest agricultural waste, and it induces huge environmental hazards to the extent that a few states starts fighting with each other. So if we can compile and we can stop these rice husks, burn it properly in a scientific manner, it can the ash can be it can be used to partially replace the fossil fuel as far as kilns are concerned. And as we all know that 1 ton production OPC releases almost equal to 0.9 tons of carbon dioxide. So let us reduce OPC, move significantly towards blended cement. And now, as just on the right hand side of this particular slide, you can see material on one side and kilogram of carbon dioxide per ton on the right side. You can say OPC is about 1 ton of OPC consumes, or rather releases 870 kilograms of carbon dioxide, and just look at the PPC and PSC. So they are almost 40 to 45% less emission of CO2 in case of PSC and PPC. So that says it all. benefits, all such technical benefits which you can envision. So in all possible ways, blended cements are far better in terms of increased strength, reduction of heat, increasing the pore volume, reducing the pore volume in concrete, increasing the water tightness, resistance to all the aggregate aggressive sulfates and chlorides, etc. So overall, a durable product we can get. And no doubt, blended cement can be used to construct buildings and structures of international repute, likes of Burj Khalifa, or for that matter, the Twin Tower in Kuala Lumpur. So entirely the concrete was used blended cement. So no one should have any doubt, iota of doubt on that. The same thing, the blended cement is going to contribute significant reduction in carbon dioxide emission. For the coastal regions also, where the susceptibility for the concrete towards chlorides and sulfates is very, very high, the potent slag cement or the potent Purjuna cement is going to be the proper reply to combat the longevity and durability of such type of concretes. Such type of hazards and structural damages can very well be avoided if we use blended cement in coastal region. Transition concrete, as you can say, these are basically non-structural concrete. They can be used in the facades or on the exteriors, etc. And it has the typical capacity to let the natural light inside of your built environment. And during the daytime, when the sun radiations are coming up plenty, you can reduce the your dependency on the natural lighting, dependency on the artificial lighting to the extent of 40 to 50%. You can minimize your electricity bills. So it's a beautiful aesthetic material. It's being used extensively in Europe and America. Or perhaps due to the exorbitant cost in India, it is yet to get a place. But maybe soon we will have this product also. Reverse concrete is the sustainable concrete. It allows the water to percolate down and recharge the depleting water tables. We are facing huge crisis. There are so many places in India. We are at the top of the summer right now, and many of the Indian villages and cities have started facing crisis of underground water. We have almost exhausted the water. Water tables have gone so deep. We are unable to get the water. So the water recharge is the only reply to that. So reverse concrete gives us excellent answer to that. Applications can be pathways, garden areas, parking areas, manhole covers. So let the rainwater go inside and recharge your water table so that the water goes up and it can be helpful to the humanity. Sand cannot be extracted till eternity. Rivers are dying, so there has to be some good alternative to sand. I would just quickly rush through these names, like M sand can be replacement. Slag sand in south, it is being used extensively. Few manufacturers have started manufacturing, and we look forward to such type of slag sand all across India. Recycled concrete aggregate, yes, it is going to be the next answer. Pond ash can be used. So by optimizing these different variations and alternatives available to us, we can minimize the dependency on the river sand and let the river live their life. They should not die prematurely. So we have got alternatives to sand. This is a sand state-wise right. Yeah. So let us move to the even the few public works department are advocating and specifying the use of M sand, because the government has realized that it is no longer feasible and to extensively, continuously explore river sand. Let us partially switch towards M sand as well. GGBS or the slag sand can be a big boost to our sand industry, or I can say fine aggregate industry. It can be used 100% individually or also in combination with river sand and M sand or the crusher dust. So these are means and ways. There are alternatives, and the best part is that NCCBM, the likes of NCCBM, NHAI, Delhi Material Corporation have all have approved the slag sand that can be used in part or exclusively in their projects. So that is a booster for the industry. As I mentioned, AC block is 100% green materials. We look forward to more of green building materials going forward. So if the AC block is only 20% of cement, cement is the only thing which generates CO2. And rest 80% is a recycled material like fly ash or other material like lime and alumina. Alumina is very, very in fraction of a percentage, and the water. So in combination of all such aggregates make AC block, and only 20% cement goes into it. So the rest, the material is again contributing towards its, being a truly genuine green building material. Good for all kinds of applications, being used extensively. Nothing new now for this particular product, has got wonderful acceptance all across. And the best part is that most of the state governments and the central government departments have started advocating and specifying use of AC block. And construction and demolition waste is going to be a game changer for India, because India roughly produces over 550 million tons of this solid waste in the form of C&D waste. Huge quantum of recycled sand and aggregate can be extracted out of the concrete waste and the building material waste, and that can be converted and they can be processed, they can be refined, and can be put into use for a partial replacement up to 20% in concrete. Now PWD and NHAI and BIS has already permitted for up to M25 grade of concrete, 20% replacement of C&D waste generated coarse and fine aggregates can be used. So that again going to reduce the quantum of extraction from the natural rivers, or maybe from the quarries. At least some flip has already been created, some kind of cushion has already been generated. So we will have at least 20% less exploration of these natural materials. Saying so, some countries likes of US, Germany, Japan, Korea, Singapore, Hong Kong, they have gone up to 90% of the C&D waste utilization. We are far behind to all these developing countries. But the positive thing is that the governments have taken a conscious call, all the way from the central government to state governments, and even the municipal corporation have also started emphasizing putting up C&D waste, recycle plants, and promoting and encouraging the contractors and builders to go to the maximum possible extent as per the BIS norms as far as C&D waste is concerned. So I will not go much into detail. These are the things that we generally look, you go across to any city or any town, such kind of waste material is observed, lying shabbily on both sides of the roads, and but nobody knows how to make use of it. But now with the latest technology and the guidance from the developed countries, we have good scope, and up to 25% in plain concrete, 20% in RCC, maximum up to M25 we can use. And as far as if it happens to be a lower grade of M15, below M15, 100% of these materials can be used. This chart, this gives us the percentages. Yeah, so I think I'm just closing on to my presentation because my time is just about to be over. Yeah, so
Yes,
all the
sir.
leading, yeah, so CPWD is now encouraging to put up a plant so that 100 kilometers from the plant area, construction site, the plant can be put up, and the builder or the contractor will be compelled to use some quantity of this waste. So the the model is already being worked. In a municipal corporation of Delhi, with public-private partnership, wonderful facilities have been developed, and good quantum of these material is being used. Yeah, so these are the different methods by which demolition takes place for the buildings and for the different categories by using different these machines. After this is implosion technique that you can see, and that is how the plant looks like as far as C&D waste plant is concerned. In Indore, we have got one wonderful facility. I have visited there, and I found that it is functioning very well. And I interacted with the process engineers over there. And going forward, the municipal corporation or the Indore Development Authority is going to put up few more plants, because Indore is a growing city. A lot of waste is being generated, but as the waste is getting generated, it has to be put into the proper recognizable use that is being done. And after the processing and washing of the aggregates, that is how you get good quality aggregates, almost as good as a natural fresh material. And these particular coarse aggregate and fine aggregates can be used for manufacturing of paper blocks, words, or tiles, etc., which is which again saves a good quantum of natural materials. Concrete waste generation of 30%. This is one of the news that I captured. This is for the Indore, and this in one of the Pradhan Mantri Awas Yojana project in Indore. The quantum of the blocks and the tiles which is being manufactured by using materials from CND waste. So that particular plant has earned almost 60 lakh rupees of revenue for the this particular company. So it has some economic sense also, and at the same time we are contributing significantly towards sustainability.
Excuse me, sir.
So with that, I come to the conclusion, and thank you very much for a patient listening. And excuse me if I have exceeded my time limits. So thank you very much for a patient listening.
Thanks a lot, Singhai sir, for your nice informative session.
So pleasure is always mine. Yeah.
Thank you, sir. And our third panelist, Mr. G.V. Ramakrishnan, was supposed to be our to deliver this webinar. This is supposed to be the next next expert, but due to someone has expired in his family, so he is not able to attend the webinar, and therefore in his place, his colleague, Mr. Gaurav Patel, will be delivering the presentation and webinar. And
Mr. Gandhi, kindly introduce the third speaker. Kindly introduce the speaker on behalf of Mr. G.V. Ramakrishna. Mr. Gandhi. Mr. Pranay Gandhi, please.
Sir, I think Mr. Pranay Gandhi has disconnected due to some signal issue.
Yes, sir.
So I will introduce myself in place of Mr. G.V. Ramakrishna. I am Gaurav Patel, working in Dalmia Cements from last 2.5 years. I am a process engineer in cement industry, and background is chemical engineering from 2004 pass out. So from last 17 years, I'm in cement industry and working for the process optimization and usage of alternative fuels, or we call it as a green fuels, for the manufacturing of cement process. So I will take you through the presentation which I prepared. Firstly, I would like to thank for giving me the opportunity, and my previous speakers have already spoken much on the usage of alternative materials in concrete manufacturing, or use of cement plus the alternative materials to prepare the concrete. My presentation would be mostly on the clinkering, how to in process of manufacturing clinker, what kinds of green material we can use and replace the fossil fuels or the natural resources, and what processes are used in that aspects. So I'll request previous speaker to please unshare it so that I can share my presentation, please. Thank you, sir. So now we'll moving from gray to green, like cement. As we all know, the cement color is gray, but the for our manufacturing process, what we do, to manufacture the gray cement, whatever resources or whatever fuels or the power which has been used is green. So we will see what kind of green I am speaking about, like for the fuels or the electricity. Also, like earlier it has been told that cement industry is one of the largest producers of CO2. So it also becomes our responsibility to capture, reduce, and make our planet green. So for that purpose, to manufacture the gray cement, we are using or utilizing the green processes to manufacture the gray cement. So earlier it was hard to abate cement sector, like it was not possible a few years back to convert, but now it has been possible to abate to capture the CO2 and use of green processes. So for manufacturing of cement, we all know we require thermal energy, for making the clinkerization. We require 1400 plus degree centigrade temperature in our rotary kilns. So it requires a huge thermal energy. Plus the electricity is also required to run the process equipments, and the material transport. Like previous speakers have also spoken, to transport the raw materials to our cement plants and transporting of our cement bags to the consumers or to the retailers. So this way there usage of thermal energy, electricity, and the material transport, which produces CO2, which is around constitutes to around 40 to 45% of to the GHG share. And for manufacturing of cement, the major raw material is limestone, so which is CaCO3. So when it decomposes to lime, CaO, and gives to CO2. So this contributes 55% of CO2 is being emitted into the atmosphere. So these are the four parameters which we are working on as our roadmap to capture the CO2 in the cement industry. So first, if they see the measures taken in the business activities, natural resources. So natural resource conservation by optimal use of industrial waste from other industry like slag, fly ash, pond ash, we use in our cement manufacturing in clinkerization. Then we have commissioned state-of-art new cement plants with latest available technologies. This has optimized our power consumption and heat consumption, where earlier it used to consume around 730 to 750 kilocalorie per kg of clinker heat. Now it has been brought down by around 10%, 640, 650 kilocalorie per kg clinker of heat is consumed because of the state-of-the-art new cement plants. Then we regularly monitor the footprint, greenhouse gases, and target settings in our organization to control the carbon footprints. The major topic which I will be taking is the alternative fuel use in cement kilns. So this, whatever dumps, whatever RDF, MSW, municipal solid waste, hazardous waste, or industrial waste which has been generated in all of the industries, around 90 to 95% of industry waste, we use it in our cement kilns by replacing the fossil fuels. New power plants based on renewable energy such as solar, waste heat is also one of the main topics, and target to become water positive. So what this has given is the less limestone and energy consumption per ton of cement, become largest producer of Portland slag cement in India, because this is the one of the blended cement which reduces the carbon footprint. One of the best energy efficiency ratings globally, replacement of fossil fuels by usage of alternative fuels or the green fuels, renewable power to replace fossil fuel based electricity. So these are the main our roadmaps for conserving the energy and also to sustain and capture the carbon dioxide. So to become the carbon negative, what steps we are? Energy efficiency, state-of-art systems have been installed, regular focus on energy efficiency, fan efficiencies to bring down our power consumptions. So these are the main aim or main criteria for this. Then resource efficiency through circular economic concept, usage of alternative fuels. So we don't use the material which can be recycled. So this we avoid using. Whatever is been after the step generated after the recycling, which is no further used to to the manpower. That fuel only we use it in our cement kilns. And deep decarbonization is the renewable energy, usage of biomass, or the carbon capture utility. Green hydrogen, solar, calcination, novel cements, these are in the pipelines. So our roadmap is switch to 100% blended cement production, use of 100% renewable power under fossil-free electricity initiatives, double energy production, use of alternative renewable biomass, bamboo, hazardous waste, hydrogen, municipal solid waste, use of electric vehicles. So if we see for thermal energy efficiency the reduction, we use the municipal solid waste or the green fuels, which will replace its fossil fuels. For reduction in energy consumption, like for the power plants, we use the renewable power energy. And to avoid the CO2 generation due to transportation, we use electrical vehicles wherever possible, and also the usage of biodiesel in heavy equipments to cut down the CO2 emissions. Carbon capture and utilization CCU to make value-added products, and carbon sequestration adoption of other advanced green technology. So initiatives which we taken is the clinker factor reduction. So by getting the blended cement, using of low clinker and making more cement. So this is one of the key criteria. So it focuses on Portland Pozzolana cement market, focuses on composite cements like slag cement, whatever different types of cements we manufacture. And also our enhancement are the developing of special cements in market, which reduces the usage of clinker in manufacturing of cement. Green power production, installation of waste heat recovery systems in our cement industries. Whatever waste heats, there are two locations where the waste heat is being generated going out of the system. One is the preheater side and one is the cooler side. So both these sides around 300-350 degrees centigrade has been emitted to atmosphere. So being an energy intensive industry, it also gives us an opportunity to capture the this heat and produces the renewable energy and also the usage of alternative fuels. So these 350 degrees centigrade temperatures are passed through the boilers, which heats the water and generates the heat, generates the power generation. So what we had done, we had installed around 72 megawatts of power generation across our units. And also we had installation of solar power plants of around 100 megawatts already. It's been done. So this way we are in the green power production to reduce the CO2 footprint. The third and important is the reducing fossil fuel consumptions, like maximizing usage of alternative fuel consumption. And our target is to reach 90% TSR, thermal substitution of fossil fuels to be replaced 90% by alternative fuel consumption, which is solid, hazardous and non-hazardous, plastic, RDF. Hazardous is the industrial waste which has been generated in manufacturing of other products, and also the liquid waste which is coming from the industries. So if we see the clinker factor reduction, so our product portfolios are OPC, which we call as ordinary Portland cement, PSC, Portland slag cement, Portland composite cement, and Pozzolana Portland cement. So where we can see in ordinary Portland cement, there's only clinker and gypsum. So which, as I said earlier, that we want to transform or focus on blended cement. So clinker plus gypsum, and here we can use 60% of slag. So ultimately we'll be replacing clinker with the slag. So this will reduce the footprints. Similarly for Pozzolana Portland, where we can use 35% of fly ash, and the composite cement where we can use mix of fly ash plus slag. So this way our clinker production or clinker consumption would be minimized, which will ultimately have the reduction in our CO2 generations. Then the next is reduction of fossil fuels, like we do the co-processing. So co-processing is usage of alternative fuels or the green fuels in parallel to the fossil fuels which we use, like coal or the petcoke in our cement manufacturing. The main advantage of co-processing is this: whatever the ash is generated by you burning of the alternative fuels, RDF or any biomass, plastics, all these materials which has been rejected or which it cannot be recycled or reused further, whatever ash is generated by burning will become the part of the clinker, and no waste is generated by burning of this waste. So this is the main advantage. Being an energy intensive industry also give, like I said earlier, it's also an opportunity for us. Based on 1400 degrees centigrade, we can burn each and every type of waste whichever is available in the market. So this is the hierarchy, like reduce. First step is to reduce. So it's our well, like earlier it was said that single person is the stakeholder. So each and every person has to step in and work to reduce the CO2. So first is the reduce. We have to reduce the potential waste. Then reuse wherever it is possible to reuse the wastage of material, the waste material. So we have to reuse it, like we had seen in earlier that the furnitures have been made, or the concrete debris which are coming, that can be reused. And the third step is the recycle. Whatever has been reused after that, whatever is saved, it can be recycled to another products, or if not possible, then only we go for co-processing. So in terms of saving of fossil fuels or the natural resources, we don't want to waste the recyclable material into just to have the gain in CO2 reduction. So it's also a prime responsibility to follow the hierarchy: reduce, reuse, recycle, and then only the co-processing. And which is not possible in co-processing because of limitations in cement manufacturing or the quality of the clinker we have to produce. Then only it will go to disposal or the landfillings. Without, as far as possible, whatever is can be co-processed, it will be co-processed, and which is not possible, then only it will go to the landfills or the dump sites. So in order to reuse, various technologies we have to implement. So different types of waste which are coming, like liquid, sludge, solids. So different steps we have to go through. We are using in our cement kilns to run the process stable and to produce the good quality of clinker, so that quality of cement can be prepared. We can use higher additives. So these all are interlinked. So for size reduction, there are shredders. We are using crushings are there, grinding. Then we have for separation. Next step is the separation, where oversized separation is done, metal separations, then air separation can be done. Mixing, impregnation or solid mixing, where we can mix liquid, sludge, and solid to make it flowable, homogenization, and the thermal preparation, right, drying it. So what we get is the alternative fuels, raw material. So this waste comes in various sizes. It comes in drums, it comes in jumbo bags. So when it passes through all of this size reduction, separation, it becomes the alternative fuel for our cement industry. So like earlier said, like preheater, pre-calciner, and main burner. So pre-calciner and main burner are the two places. So according to the firing location, we have to prepare the material size. So if drums are there which are around 1 meter height, it has to be reduced to 50 to 60 mm of size. So combustible in our cement kilns, and we also gives us the cement process stable. So if we can see here the size of material, so more the smaller the size we do, so the cost of operating cost of that particular material will increase. So this way it's also important to make the optimum usage of pre-calciner first, to and the size of the material to gain the benefit from the usage of alternative fuels. So these are the alternative facilities we have installed. The material which comes been used by the heavy equipment goes to the shredders. So all there are imported shredders. After shredding, the material separation is taking place. The metals are separated. Then the screening takes place, where the smaller size material is screened and the oversized materials are again recycled back to the shredders. So what ultimately we get is the less than 80 mm of size of material, which is fed through the feeders to our pre-calciners through double flaps of feeding to the calciners. So in Dalmia Cements, we had installed around 9 shredders and screens, 100 tons per day of capacity. So our present consumption, if you can see, we are consuming around 3,000 to 4,000 tons of plastic, RDF, hazardous materials per day in our cement kilns at around 8 locations. In liquid feeding systems, we had installed 3 numbers, which we consume around 100 KL, 100 tons per day of capacity. So this is the quantum of waste which we consume in our cement industry, which brings down which helps the community by reducing the the dump area where the huge stock of RDF or the biomined RDF was stored. So there are other challenges which comes with the RDF or the MSW, which our household waste are also there. So it's high moisture and ash. So there's moisture in this process and also the ash which is coming. So installation of RDF dryer for reduction of moisture and exploring the system for separating the ash. The other major component is the chlorine which is present in plastic and RDF. So this also limits our process to consume on higher volumes without doing any further investment in our cement process manufacturing. So if higher the chlorine goes into the cement, more than 0.1% in cement, if it goes, then there will be a corrosion issues on the longer run for our beams or the pillars which you have prepared. So to minimize the impact on process clinker, we have to install chloride management systems. So chlorine bypass systems have been installed so that we can take higher amount of chlorine into our system and thereby reducing the CO2 footprints. So consistent feeding and granulometry, we had already seen that how the size is very important in order to feed into our cement kilns and also to have the stable cement process. So how we do our business is that business to business, B2B. So we have ties up with plastic mills, FMCG companies, aluminum industries, Vedanta, Hindalco, and many more industries. So we get directly waste from these industries. We do the pre-processing with the help of shredders and systems available with us, and then we feed to our cement kilns. Other is business to government. So we had ties up with various municipalities, government-owned industries. So we get the waste from them, we shred the material, we blend with the available other industry waste and prepare it suitable for our cement kilns. So this is our road target where capacity, what kiln system modifications we do, chlorine management system, chlorine bypass system. And our group target by next year is 30. And by 2025, we will be around 50% of thermal substitution rate, where we'll be replacing 50% of fossil fuels with the alternative fuels or the industrial waste which has been generated. If we go for green power production, is that by 2023, we will be a total of 72 megawatts of WHRS capacity. So already by 2023, 40.8 it will be added. Similarly, for solar capacity, by 2023, by next year, it would be 101 or 100 megawatts of power which will be generating. The other is the carbon capture technology. So what is our view that policies to be supported like in US? So government has to step in to support the industry to make the policy which will be useful for CCS technology. The land and infrastructure rights needed is difficult for private sector. Then CCS only possible with government infrastructure supports in big way, and EVs to be replaced by IC engines. And CCU technology like CO2 recycling pathways could deliver deep emissions. The if you can see here, the geological storage sites has to be mapped where we can store the captured CO2. Driving demand in core sectors like renewable energy, green hydrogen, so all this. And the challenge is the high cost and acceptability. So capturing CO2 is a high cost, and then economically balanced also has to be seen by the cement industry for the, getting into sustainable waste. So these are the key products possibilities or the feedstocks. You can see hydrogen, process, water electrolysis, feedstocks. So there are many desired products, process, and the feedstocks which comes out. This is the main carbon negative roadmap. So like India has pledged by 2050, but we our internal target or the by Dalmia's vision is by 2040, 10 years before, we want to be the carbon negative. And even today we are the lowest carbon emitter cement industry, whereas global sector is 900 to 1100, but we are around 450 to 500 per kg CO2 per ton of cement we produce. So by 2040, we want to be the negative carbon emitter. This is our internal target. So this is the main message we would like to give. There's giving back to the motherland or the environment needs patience. So never give up on the sustainable solutions or to reduce the carbon footprint. Thank you.
Thank you, Mr. Patel, for the very nice session. I would like to invite Shri Deepak Shah Sahab for vote of thanks. Shah Sahab, can you hear me?
Yes,
Yes, sir, kindly extend vote of thanks.
oh, actually in between I could not connect.
Okay.
So question answer session.
Okay, let's take question answer session first. Yes, any questions from the participants? Anyone want to ask any questions to our panelists? Okay, I think
two questions are there in the board, sir.
Okay, please carry on. Okay, please carry on.
Sir, to Mr. G.V. Ramakrishna and Mr. Patel, what is the current clinker cement ratio for typical cement production in India, and what, if any, is the target to improve this? Patel, sir.
Yes, sir. Like I had always shared that various blended cements have been prepared. So in the around 65% clinker is being used for the PPC. So it can be reduced by usage of slag cement. So presently I can say it's around 50 to 60% is the clinker usage in making the cement. So there are plans to further bring down the usage of clinker in cement manufacturing by increasing by the usage of PSC, Portland slag cement, and various other cements in the market.
Thank you, sir.
Welcome.
Shah, I think there are no more questions.
Okay. So on behalf of Indore Local Center, I wish to extend my sincere thanks firstly to all the panelists, Imar Kalgal Saab, Ashish Singhi Saab, and G.V. Krishna Rao ji. So it has been a wonderful session so far as the sustainability in the cement and concrete industry is concerned. So I think the participants have benefited quite a lot, and it appears from the number of participants also that they are in such a good numbers. So I wish to thank all the panelists. I would also like to thank the convener of the program, Engineer Pranay Gandhi, for arranging such a wonderful session. Thank you, all the participants. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you. Thanks a lot, everyone, and good night. Bye bye.
Thank you.
See you.
Thank you very much for inviting me. Thanks very much.
Welcome, welcome, welcome. Most welcome, sir. Most welcome.
Thank you, sir. With kind permission from the
Yes,
chair
sir.
and the moderators and
Pardon?
panelists of the session, we are now concluding the session.
Pardon? Okay, sir. Okay.
With the kind permission from
Okay,
all
sir.
the chairs, we are now concluding, sir.
Pardon?
With kind permission from all the chairs and the moderator and the panelists of the session, we are now concluding.
Yes, sir. Permitted.
Oh, yes, sir. Okay. 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 Please carry on. Thank you.